Alright, so this morning we'll be looking at how we go about assigning static routes and what the differences between the various versions of static routing is. So we'll look at configuring both IPv4 and v6 static routes and default static routes. And with the default routes, we'll have a look at how to configure it so that we have a backup option as well. So we do this with adjusting the weight. So we'll go over all the little bits and pieces. Now, static routes work really well in small networks where we don't have a lot of option for directions we could take. So if we've only got one out, it's quite often that we'll put in a default static route pointing upwards to the internet or towards the gateway. So these small networks can handle static routes very well because we don't have to do a lot of manual configuration. And we'll look at how we go about issuing everyday static routes, so putting in a route so that we can see networks that we need to get to, default static routes and how they differ only slightly from standard static routes. Then we'll look at putting in floating routes, which we do a little differently, and summary static routes. So how do these work? Well, we configure them via the IP route command. Now, just as with every other IP change, we have IP version 4 as IP and IPv6 as the v6 version. So IP route or IPv6 route, and the syntax is basically the same, just the addressing form changes. So when we configure the address for the network we want to connect to, we point it to the next hop, which is the next device that has to handle the routing of the traffic. Now, this is done via the IP address of generally the closest interface of that router. The other way we can do it is to give it the exit interface that we need to send it out. Then the fully qualified, if you like, is where we not only give it the next hop address, but the exit interface that it has to be sent out of. This is the best option, because what happens for the other two is it has to do a secondary lookup. So in the first one, when we give it an IP address to send it to, it has to do a secondary lookup to find the network that it belongs to and make a forwarding decision. When we just say send it out of the interface, it's going to work out where to send it to along that path. So it's a little bit different. So it's a global config command, IP route, the network address that we want to send traffic towards, followed by its subnet mask, and then we define the next hop IP address or the exit interface. If we're defining the exit interface, we can then define the IP address that is associated with the link. Following that, is the distance. Excuse me. The distance is administrative distance, which is like the, well, keep it in the same terms as what we'll do for the next one for the routing protocols. The administrative distance is how trustworthy the route is. So what we can do with the distance is say how the priority is A to use this route. So within the distance value, we tell it the order that it will make use of this route that we've just entered. Same syntax for IPv6. We just change the address fields. So we put the IPv6 prefix and the prefix length plus the exit interface. So exactly the same format of the command, just with the IPv6 addressing entered. So we're going to use dual stack routers in this instance and talk about how to set up addresses for this scenario. So looking at router 1, we would have a directly connected network, which is the local area network. So let's step back again. So this one down here, this is what we're looking at. So we're looking at PC1's network connected to R1 and the serial connecting to R2. So with that, we have the 162.16.2 network connected to the excuse me, serial line going up to R2. And then we have the directly connected network 172.16.3.0/24 connected to our switch and the rest of our PCs. And we can ping router 2 interface and get a reply because it knows how to get there and get back. Whereas if we flip back, so when we ping here, we get a response. Ping here, we don't. Because what happens for it to ping this interface is it has to actually go here and reply. Gets a little messy. So as a reminder, the ping command is actually designed to check connectivity between end devices. It gets a little confused when you're checking a point-to-point serial link because both this device and router 1 and router 2 need to know exactly what's going on with both the addresses, and sometimes the actual underlying technology that is providing that serial interface can't resolve the address and actually respond. That's normal behavior. Again, remember the same commands in IPv6. Now the difference here is they actually use the correct ping commands to try to ping router 3. Now, the other issue, as I said, the inability to respond if you ping a directly connected interface. Sometimes it doesn't respond on those serial links. Just remember that when you go into troubleshooting later on. 90% of the time you'll get a response. But just register in the back of your mind, occasionally you won't. Because with some of the technologies that you won't see as often anymore, such as frame relay and ATM, they don't resolve automatically at layer 2. They've got to be mapped. And if that mapping is a little off, you can't actually get the layer 2 to layer 3 mapping registered, and it doesn't know how to treat the ping request. In the instance of what they're trying to say, but have made the mistake, is that one there should have been the IP address on router 3, which wasn't the case here. So the actual address they should have been trying to get was 1.1, this interface here. Now, what they did was actually type in this one here. So they got the response that I would expect. So how do we make it so that the address can ping back? Well, what you have to do is to configure a static route on router 1 that point to all the other networks that we want to get to and get back from. So you've got to put in a route for the 172.16.1.0 network and give it the address that it can go via to get to that network. The same with the 192.168.1 and 2 networks. Now you'll notice they are all pointing to the same address. This is the closest interface of the next device that needs to make a forwarding decision. So what it's saying is, if it isn't a directly connected network, forwarded to the next device, if it's a 172.16.1.0, 192.168.1.0, or 192.168.2.0. Now, the other thing I'd like to also remind people of what the L is. So this is the connected network, and the L came about when we made adjustments for IPv6. This is the IPv4's version of a link local address, which is the address of its interface. Alright, so when we did the modifications for IPv6 in the operating systems, we had to cater for 2 addresses each interface, which would be our global one and our link local one. So to keep the displays consistent, they modified how it displays directly connected interfaces. It would automatically insert the local as well as the connected network that it belongs to. Here we go and configure IPv6. This has to be turned on as a first command because unicast routing is not on by default. So you need to turn on IPv6 routing and then you can put these static routes in. Now, router 1 now has the static routes for all the other networks, but we still won't be able to ping them. Why? Because the other devices don't have a return route. Alright, so we have the networks listed in our routing table and we know how to get there, but we don't know how to get back. So you need to rinse and repeat on all 3 devices for the remote networks. Next, we'll be looking at the command for using the exit interface. So as you can see here, we generally just use the same structure, but we're specifying the exit interface. Same with IPv6. Now to get into the fully qualified, so this one we put in the network, subnet mask, the exit interface, as well as the next hop IP address. This means the route is fully qualified. In other words, we give it the network address, the next hop address, as well as the exit interface. So it doesn't have to do any more calculations to work out how to send the traffic. So it looks at the network, gets a match on the remote network. It knows which device to send it to and which interface to send it out of. All in one line. Now, this is where IPv6 syntax becomes a little different to our standard command. We need to use the link local address for the next hop when we're using it in this format. So when we specify the exit interface, we need to then follow that up with the local address for the device we're connecting to. Okay. In the first example, when we were just putting in the next hop address, we were using the full IPv6 address of the next devices. So we use the ACAD2:2 address. But when we're using the exit interface in combination with router 2's interface address, we need to use the link local address to point it to this device. That's the only qualifier on IPv6. There's the output of the show IPv6 route static command. With entering static routes, the usual show commands are in place. So show IP route will show you the routing table. You can then define the output by showing only the static routes or the specific network that you want to see. You could use the show running config and then qualify the output with the section IP route, which will list all the IP routes commands together. You then can use your ping and trace route commands to prove connectivity after that. Now, a default static route is a special one. What we're doing is we're configuring a catch-all. Now, I'll remind you that when we're looking up the actual static route itself, we go through the routing table and look for a match with the longest bit match as possible before selecting that route and forwarding to the destination. What we're doing with a default route is telling it, no, you don't actually have to match anything precisely. So if you do not get any matches in the routing table, and where you would normally discard the packet, I'm going to have you forward it to a neighbor so that that neighbor can make the forwarding decision, hopefully with a bit more clarity as to where to send it. So we would generally use this scenario in a stub network. Now, a stub network is where we only have one way in, one way out on the router. So we have our directly connected network, and then we have our one way out to the rest of the network. So what we can do, rather than having an active network, we can have a default gateway pointing up to the exit, and all traffic will be sent there without having to know the precise networks that are available via that other device. So what makes this default route a special one? Well, it's the quad 0. In other words, it's the one that doesn't match any bits. So its default route is IP route, quad 0, quad 0, and then the next hop address information. So this makes your default candidate route. Now, what is a default candidate? Any network can be used this way. Now, what happens is I can have 2 default routes if I'm multi-homed, but I want to send traffic via one specific location. It needs to make a choice as to which one to send the traffic to. So that's why it makes it a candidate, and then out of the candidates, it chooses the master default. So the IPv6 version of it is where we have : which is all zeros, /0, and then the next hop. So here we have examples of it. So on router 1, we say IP route quad 0, connect to 172.16.2.2, which is router 2. Rinse and repeat format for IPv6. So when we look at it in the routing table, it's going to be an S for a static, but it's going to have this little asterisk next to it. This asterisk means it's a candidate for the default route. Now, behind the route, quad 0, is this little square brackets. This is the administrative distance and the cost of using it. Now, if I had more than one static route with the asterisk, this first value would determine which one I would use. Admin distance of 0 are directly connected networks. Manually configured networks default with an admin distance of 1. But we can change that value. Remember that little distance option at the end when we talked about the original syntax of the command? So that's where I could multiple defaults, but I could have a different admin distance. So there would be a possibility of 2 static routes that could be used as my final gateway. So each selects one of the candidates and makes it the gateway of last resort, which exists outside of the routing table between the codes and the actual routing table. So in other words, if there is no match within the specific routes in the routing table, it will use the gateway of last resort to send the traffic rather than discarding it. Works exactly the same way with IPv6 in that it becomes a static. Okay. And I will use this as its option because it doesn't have to match any bits. It'll match it as a route and forward traffic because there's no longer match than that one. And here comes where the floating static routes come in. This is where we use that admin distance, as I was talking about in the examples, to create floats. Now, only the one that it selects as the best will be displayed in the routing table. So if we have equal costs to the same destination, it'll list multiple entries. But with a floating static, what we do is we create our secondary static route with an administrative distance greater than 1, meaning it's floating and will only appear if the primary disappears. So the only cost lower than 1 is 0, which is basically reserved for directly connected networks. So it only trusts its directly connected networks more than the networks that we assign as administrators. So what we want to do when we want to create a backup to this primary default route is put it in with a higher admin distance, and it becomes active when the first primary fails. So here we put in our first primary, IP route quad 0, 2.2, and as we don't specify administrative distance, I'll go in as 1. Second line here, IP route quad 0, but we're pointing it to another device, 10, 10, 10, 2, with an administrative distance of 5. So what appears in our routing table is the route to the same destination that is trusted more, which means the one with the lowest administrative distance, which is 1, so the 2.2 address. If that fails, it'll then use the second address. So what happens if it fails? So router 2 shuts down. Alright, we lose connectivity to router 2 for whatever reason. And router 1 generates a message saying the link to router 2 is gone. So as soon as router 1 loses this link, it now knows that all the routes in its routing table that are dependent on this link have now become invalid. And it'll cut over to its secondary routes. So it looks up in its database of all the networks, and it'll find it has a secondary route to the same network. It'll activate that secondary route. This non-preferred route, because the administrative distance is higher, therefore it's not as trusted as the first one. First one's become invalid because the links got shut down. So the secondary one becomes valid and is inserted into the routing table. Host routes are where we use the /32 in IPv6 or, try that one again. /32 in IPv4 and /128 in IPv6. Maybe I should go back to bed and get some more sleep, and my tongue might catch up with my brain. So basically, these are the local addresses that are configured automatically. They can also be used to configure static routes, and they can also be used by dynamic routing protocols, which we will go through in another module. So, and it won't be the next one, just to give you a hint. So when we actually look at the third part of the CCNA course, that's where you'll find about these other routes that are automatically obtained. So by default, the automatic routes that it will insert are our directly connected networks and our local routes displayed as an L. So this for IPv4 is the configured IP address on the interface that is connected to our C. So our C, our directly connected routes, is the network that exists on that interface. That contains the accurate subnet mask. The interface address is specific to just that interface, so it matches all 32 bits of the IP address and injects that into the routing table. Now, when we configure addresses, this can be used. Now, this is a specific type of routing that matches a precise address. Now, we can also use this in other ways, as it said. One of the ways it will generate a /32 address is if we generate an IP address for a loopback address. And I'll show you those later when we go through ENSA, which is the third course of the CCNA sequence, and how we use that in dynamic routing protocols to generate more remote networks for testing, and how we use it in OSPF to uniquely identify each device within the OSPF process. More on that in the next series of videos called ENSA, which is the one that does with routing protocols, security, and combines all of our unique troubleshooting together and a couple of other bits and bobs such as DHCP, NAT, so filtering. So it's an interesting course all on its own, but that's next year. Alright, so moving on. How do I configure it? No different, it's just a static route. Alright, so what we're doing is we're going to say this is the IP address of the device, and you need to match all the bits. So it's 255, 255, 255, 255. And then the next hop address. So this is a host route. Normally we put the network address followed by the subnet mask of the network. Now when we do a host address, it's all equivalent to a network address, because that's how routing tables work. They only display routes or networks. So to have a host route, we have to say that the host is a network. We use the same commands to verify host routes as we do any other route. So the show IP route commands, ping commands, trace route commands. Okay, so it's the same as we do now. With the IPv6, remember it gets a little interesting, and when we forward to the address, we have to specify the exit interface and its local address of the connected device. There are several packet tracer activities for you to do within this module. It'll give you a good understanding and help you remember the syntax of the commands if you go through them. And in summary, what did we go through? We looked at why we use static routes and why we use slightly different formats to achieve slightly different desired outcomes of the static route. So to bring it all together, IP route, the network that we want to send traffic to with its corresponding subnet mask, and then the next hop address, or the exit interface we need to use to connect to the next hop, with an optional IP address specified if required. The other optional parameter is the admin distance. By default, it'll be 1. If we want to just use the IP address of the next hop, that's fine. That's all what we have to do. If we want to specify the exit interface, we just can do that as well. We would normally only use that on a serial line. If it's a multiple access link, in other words, it's not point to point, we would specify the exit interface followed by the IP address of the next hop. That's where we use the specific fully qualified address. We looked at the fact that the syntax of this command structure is the same. Doesn't matter if it's IPv4 or v6. We only change the addressing parameters. We then had a look at what makes up a default route, which is the quad 0. Why we use the quad 0, so that when we don't have an explicit match in the routing table, packets would normally be discarded because it's had no match, so it can't forward traffic, so it's discarded. If we have a default route, when there's no match in the rest of the routing table, it'll match the default route and forward traffic. We then looked at the fact that we could create floating static routes, in that the secondary ones, the ones with a higher administrative distance configured, would be backup routes that would be activated if the link to the primary failed. We then had a look at what they are called host routes, where the entire address space is considered network space. So the 32 mask is used to signify the network portion. These routes are used to signify a specific device that we want to get connectivity to. So these devices would then be listed in our routing table and can be routed directly to that device. We know that routes can be entered in automatically when we configure the interface, static by us being configured, and dynamically via other routing protocols that we'll look at in the next course. The new versions of operating systems will install a host route for all of its local connected networks. And the other thing we looked at and talked about was the fact that the only syntax difference in the default static route commands is when we use the format of exit interface and IP address for a fully qualified route in IPv6 is we need to use the local address of our next hop device in this format. So that's the FE80 address of the next hop device. That's the only quirk difference between IPv4 and IPv6. That concludes Module 15 or Chapter 15, and we'll be doing Chapter 16 next, which is troubleshooting static routes.